This lesson is about elastic forces. Let's talk about Hooke's law applied to springs and elastic strings. So before talking about Hooke's law, let's talk about deformation. So deformation is a change in shape due to the application of a force. If we apply a force in a spring or in a string, and if it's in an elastic situation, we can apply Hooke's law. Hooke's law says that the force equals the elastic constant times the deformation. We can apply Hooke's law in springs and in elastic strings, for example. Another very common application is in a thing called the dynamometer. This thing here let us know the force based on the displacement of a spring. So we have a spring, we can hang something here that we want to know the weight force, and based on the displacement or the deformation of this spring, we can know the weight. If we know the elastic constant of the spring and the displacement, we can then calculate the weight force of an object we add here. We can also use some different springs arrangements. We can basically put springs in series or in parallel. In series, we have two different constants here, two different elastic constants. And to use it in the Hooke's law, we have to find an equivalent constant. And we know that this equivalent constant, actually the inverse of this equivalent constant, equals the sum of all the inverses of the springs that we put in series here. In parallel, it's pretty similar. If we have these two springs here in parallel, for example, we can calculate this equivalent elastic constant just by adding all the elastic constant of the springs that are in parallel. Okay, let's put our knowledge in practice now. So we have this system here of two blocks connected by a spring that's resting on a smooth and frictionless surface. We know the masses of A and B, that are 4 and 2 kilograms respectively, and that the spring has a constant of 100 newtons per meters, and also that the natural length of this spring is 30 centimeters. We want to calculate the system acceleration, and the new length of the spring on a force of 30 newtons is applied on block A. Alright, for the acceleration of the system, we can just apply Newton's second law of motion, and well, let's neglect the mass of the spring here. So we have that the total force equals the mass of A plus mass of B times the acceleration. We know that the total force is 30, mass of A is 4, and mass of B is 2. We can then find an acceleration of 5 meters per second squared. Now for the new length of the spring, let's use Hooke's law. And let's apply it on block B here. Alright? So we have that the force on B can be calculated as the mass of B times the acceleration, and it's also the same force as the spring is applying on block B. So it's the constant, the elastic constant, times the displacement. In this case here, we have the mass, we have the acceleration that we found before, we have the constant, and then we find a displacement of 10 centimeters. We also note that this total displacement is actually the final length of the spring minus the initial length. We know the deformation here, and we know also the natural length of the spring is 30 centimeters, so we have a new length, the final length of the spring of 40 centimeters. Okay, so it's your turn now to think a little bit about it. Look at this image here. We have a dynamometer, and that's right beside a ruler. So consider that the natural length, the initial length of the spring is this size here. The spring, the natural length is 4 centimeters, all right? So based on this picture here, can you calculate the constant K for this spring? Think about it and write your answers in the comment section.
Now that you've learned the theory, it's time to put that to practice. Check out our next videos for practical problems.